So good evening. So today we will see the problem solving session 9 on the topic memory separation technology. So here is a brief recap. Various models and application design aspect in electrical field, enhanced membrane separation process, then micellar, enhanced ultrafiltration. So based on these topics, so I'm going to take questions first MCQ, then numericals. So starting from the MCQ one, the question one, which of the following is the key design parameter in a membrane separation process? Right? Check the options. So generally, membrane surface area, it affects affects the flux and efficiency of the separation process. So larger the surface area, higher the potential capacity of the separation process. So option B is a correct one. Question 2. The electrical field enhance the membrane separation process aims to improve the separation by. So, in the electrical field enhance membrane separation process, so use by means apply the an electrical field to improve the separations. So, option C is correct one. Move to the question number 3. In electrical field enhance membrane separation, the phenomenon of electrophoresis refers to. So generally, electrophoresis is a moment of the charge particles under the influence of the electrical field, right? So charge molecule can be driven towards the or away from the membrane. Option B is a correct one. Question 4. What is the primary role of surfaction in micellar enhanced ultrafiltration? Micell, micellar, right? So generally, the surfactant are added to the feed solution to form the micelles. So these micelles can encapsulate the hydrophobic contaminant, increasing their size and making them easier to filter out by the ultrafiltration membrane. So here is a option B is a correct one. So it means form the in this question has the primary role of the surfactant. So to form the micelles that trap the contaminants, so that help us to uh, easier separations. Moving to the question number 5, which factor most significantly affect the performance of the micelles enhanced ultrafiltrations? So here the concentration of the surfactant affect affect the performance of uh, micellar enhanced ultrafiltration, because if concentration of the surfactant is low, so might not form a sufficient micellar, and surfactant concentration too high, so it could will lead to the micelles aggregation and clogging the clogging of the membranes. So option D is a correct one. So moving to the question number 6, what is one common application of electrical field enhanced membrane separation process? So generally, so this electrical field enhanced membrane used in the biotechnological applications, so such as the protein separations. Option B is correct. Question number 7. In the design of the membrane separation process, the flux of the membrane is influenced by. So the feed concentrations. So it influence the driving force for a transfer across the membrane. And second is a pore size. So means control the size of the molecule that can pass through the membranes. So option C is correct one. Question 8. What is the main advantage of using micellar in an ultrafiltration over the conventional ultrafiltrations? So here the question asks what is the main advantage of this micellar enhanced ultrafiltration over the conventional filtrations? So conventional ultrafilters struggle with the smaller particle and nonpolar contaminant due to the uh, inability their inability to form a stable particle for the filtrations. So this missile enhanced ultrafiltrations ability to filter out the smaller particles and nonpolar contaminants. Option B is correct. Question number 9. Electrical field enhanced membrane process can help mitigate membrane falling by. So check the option applying higher mechanical pressure, no, using smaller membrane portion, no, repelling the charge pollutant from the membrane surface. So this could be possible by applying the electrical can repel the charge particle or pollutant from the membrane surface and reducing the fallings and increase the longevity of the membrane surface. Option C is correct. Question number 10. In a micellar enhanced ultrafiltration, increasing the feed flow rate will typically. When feed rate increase, the driving force across the membrane also increase and also permeate flux also increase. So however, at the flow rate is high, it could cause the concentration polarization and reduce the separation efficiency. So option C is correct. So increasing the feed flow rate increase the permeate flux. Question number 11. Which of the following separation mechanism of the gas separations? So savings and size exclusion for the ultrafiltration and microfiltration. UF, right? Solution diffusions is a reverse osmosis. This mechanism for the reverse osmosis and sorption diffusion is for the gas separations. This mechanism for the gas separation. So option C is correct. Question number 12. If the ideal separation factor of mixture A and B is denoted by the alpha AB, so equal to the ones, the actual separation factor should be, right? So alpha AB equal to ones means two component have a same volatility. So in such uh, in such way that the actual separation factor alpha AB would also be 1 because there is no driving force for the separation of the two components, right? Option C is matching here. Alpha A B less than 1, it means B is more volatile. B is more volatile than the A, and See, alpha AB greater than 1 means A is more volatile, but there is no condition to match with this ideal separation factors. Option A is correct. Question 13. What are the cleaning technique for the removal of the membrane fouling? Mostly the air flushings and the chemical flushings mostly used for the cleaning technique to remove the membrane fouling. Question number 14. Which method is used for the separation of the azeotrope mixture? So here is the pervaporation. Which method used to separation of the azeotrope mixture? So question number 15. So it's a numerical. The ideal separation factor of B over A for a diffusion through a polymer film is alpha BA equal to 4.5. The permeability of A is a PA equal to 3 barrier. What is the permeability of a B? Right? Here is a ideal separation factor given B to A 4.5 and permeability of A given. So we have to calculate the permeability of the B. Right? So the ideal separation factors alpha B A equal to permeability of B divided by permeability of A, right? So here permeability of A given and this separation factor given. So I have to calculate the PB. Right? So 4.5 into 3. So 13.5 barrel. Moving to the question number 16. A membrane filtration system process 500 liter per hour of water. The membrane has a permeate plus 20 liter per meter square per hour. Calculate the required membrane surface area to process the water at this rate. Right? Here is rate given and flux. Right? Divided by area. So you have to calculate the area flux given. So A is a 500 20 is equal to 25 meter square. So this is the surface area of the membrane. Means required the surface area to process the water at this rate. Question number 17. In electrical field, enhance the membrane separation process. A membrane operates under an electrical field of 0.5 volt per centimeters. The distance between the electrode is 2 centimeter. Calculate the voltage applied across the membrane. The voltage V applied across the membrane, the V equal to E into D, right? Here E is a electrical field and D is a distance between the electrode. And V is a voltage applied. Voltage applied across the membrane. Right? So V is equal to electrical field 0.5 V1 to 2. So 1 volt. Moving to the question number 18. In a Massler enhanced ultrafiltration process, the feed flow rate is 300 liter per hour and the membrane surface area is 15 meter square. If the flux through the membrane is 18 liter per meter square per hour, calculate the actual permeate flow rate. To calculate the here is a flow rate given, flux E given, and area given. Now we have to calculate the actual permeate flow. So to calculate the permeate flow rate, QP, right, flux into area, right. So 18 into 15. Meter square, so 18 liter per hour. Flow rate. Okay, you have flow rate 270 liter per hour. This is the actual permeate flow rate. Question number 19. In the Massler enhanced ultrafiltration system, 200 mg per liter of the surfactant is added to the feed solution of 500 liter. Calculate the total amount of surfactant in grams required for this process. So here is a concentration given 200 mg per liters added to the 500 liters solutions. Means you have to calculate means how much amount surfactant required for this process, right? So total amount of surfactant denoted by the EM, right? Concentration into volume. Concentration of the surfactant into volume of the solution. Concentration 200, volume 500 liters. So 1 into 10 to the power 5 mg. So then in this question asked the in a grams. So convert into the grams. So it's a 100 gram. Moving to the question number 20. A membrane separation process operates with the initial pressure is 5 bar and final pressure 2.5 bar across the membrane. Calculate the pressure drop across the membrane, right? So to calculate the pressure drop, this is P initial minus P final. Yes. Delta P equal to 5 minus 2.5. So 2.5 bar. The question number 21. The permeability of the carbon monoxide in polysulfone film at 25 degrees Celsius is a 0.3 barrier. What is the permeability value in the gram mole into meter per meter square or into second into Pascal, right? So here is a given the unit of the permeability in bare air. We have to convert into gram mole this way in this unit, right? So here is a one barrier equal to 10 to the power minus 10 into unit is centimeter cube at STP standard temperature and pressure into centimeter per centimeter square volumes into centimeter Hg into second, right? So at standard temperature and pressures, this temperature is 0 degrees Celsius, pressure is a 1 atm, right? So 1 centimeter cube of gas at STP, the 4.46 into 10 raised to the power minus 5 mole. So it will get by the PV is equal to NRT, right? So N by V, right? N by V. So 1.01325. So N, right. So T by RT, right? P is the 1 atm and T temperature is a 0 degree Celsius. So it will get the this value. And the 1 centimeters Hg is equal to 1333.2239 Pascal, right? And centimeter you have to convert into the meter, 1 into 10 to the power minus 2 meter, right? Now first we convert this one barrier, then we multiply by 0.3. So right, so it's 10 to the power minus 10 into 4.46 10 to the power minus 5 mole, right? Into, here is a centimeter convert into the meters, right? Here is a centimeter H equal to 133.2239, right? Here is a centimeter square convert into meter square, 1 into 10 to the power minus 4, right? So here, so calculating, you will get 3.345 into 10 to the power minus 16. Unit is gram mole into meter divided by meter square into second into Pascal, right? Now here is the given 0.3, so you multiply, so you will get multiplying 0.3 into these terms, so you will get 1.0 into 10 to the power minus 16. Unit is the same here. So option E is the correct one. Moving to the question number 22, an experimental data on a batch ultrafiltration of milk using a proprietary asymmetric membrane could be correlated to express the permeate flux as a function of the permeate volume at a constant delta P. So here is the flux given relations. JW is equal to 2.5 into 10 to the minus 5 Vp raised to the power minus 0.2. Right? Unit given Vp permeate volume. Calculate the membrane area if 1 meter cube of milk is to be ultrafiltered to half volume in a 1 hour batch. So the flux JW equal to 1 by AM dV by dt, right? So permeate flux as a function of the permeate volume, right? So now dV, arrange it dV P right here. P is a permeate volume, dV P by dt equal to AM JW. Rearrange it, right? And is there a feed? Feed is a 1 meter cube, right? Permeate is equal to 0.5 meter cube. It's a half is mentioned. And time is a here is a hours, so convert into the seconds. Right. Now to put the this here this value here means this relation in these equations. So dVp dt equal to AM into 2.5 into 10 to the power minus 5 Vp minus 0.2, right? So take this term here, is right left side. So dVp, these terms, so Vp minus 0.2 and dt right side. So AM 2.5 into 10 to the power minus 5 into dt. Now we have to integrate terms 0 to 0.5 and 0 to 1 hours, right? So integrate this one. So 1 by 2 Vp 1 by 2 1.2 with a limit 0 to 5, right, equal to AM into 2.5 into 10 to the power 5. This is right. So just you have to solve this one. So AM after calculating So you will get a AEM equal to 4 meters square. So calculate the membrane area, the 4 meters square. Moving to the question number 23, the feed side of the membrane gas separator has a equimolar mixture of PS2 denoted A and CH4B at a 30 bar total pressure. The product side is at 1.1 bar. The product side is a 1.15. The membrane asymmetric thickness is 0.2 micrometers. Permeability PA given 30 barad and PB 0.12 barad. So here we have to calculate the first one. If the downstream pressure is considered to be much smaller than that of feed side, so calculate the product loss and its the composition. In second part, compare the ideal separation factor with the actual calculated without neglecting the permeate side pressures. Right. So in this question, given the sorry, permeability PA 30 by PB 0.12 barrel, right? And P1 is a this is a P1, right? This is a P2. Here is the equimolar mixtures means XA XB equal to 0.5, and here is the thickness given 0.2 micrometers. So convert into the centimeters. So 2 into 10 to the power minus centimeter. Right. So here, if the downstream pressure is considered to be much smaller than that of the feed side, calculate the product plots. So here is the assumptions. P2 is less than the P1. So now flux of A, to calculate the flux of A, JA equal to permeability of the A divided by LM. This is the thickness, membrane thickness, to P1 XA P2 YA. So here is the P2 is a less than, so system get cancels P2. So JA equal to is a unit of P is a, sorry, permeability unit is given the barrier. So you have to convert into like so we will simplify, and 30, right, to 10 to the power minus 10, right, and LM 2 into 10 to the power minus 5, right, into P1 is a 30 into 0.5. So it is a 30 unit of pressure is a bar. So you have to convert the centimeters Hg, right? So multiplied by 75. It's 1 bar equal to the 75 centimeters Hg, right? So Ga is equal to 0.168 meter cube at STP divided by Okay, sorry, centimeter cube. Where is centimeter square into second, right? Now how to convert this centimeter cube into the gram mole. So here, this last question is uh, 1 centimeter cube of gas equal to 4.46 into 10 to the power minus 5 mole, right? So multiply by this one, so that's you'll get 7.54 into 10 to the power minus 6 gram mole per centimeter square into second. So here is a unit given centimeter cube at a STP. So to convert into the gram moles, so you have to multiply this value. So general, uh, 1 centimeter cube of gas equal to the 4.45 4.46 into 10 to the power 5 10 to the minus 5 moles. So we'll get this value in this unit, right? Now JB divided by JA, flux of B divided by flux of A equal to permeability of B divided by permeability of A, right? So we have to calculate the JB, right? So PB given, PA also given. So J is recently calculated, so we have to calculate the JB, right? So JB equal to JA into PB, PA, right? It's a 7.52 into 10 to the power minus 6 into 0.12 divided by 30, right? Seven. So you will get the value 3.08 into 10 to the power minus 8 gram mole per centimeter square into second, right? So we calculate the product plus. Now we have to calculate the composition of the permeate, right? So to calculate the compositions, Y is equal to JA divided by JA plus JB, right? So J, we calculate the J and JB. So put in these equations, so we get the composition of the permeate is 0.996. This is the composition of the permeate. Now moving to the second part. Compare the ideal separation factor with the actual calculated without the neglecting the permeate side pressure, right? So here is the formula given to calculate the actual separation factors. So the path to calculate the ideal separation factors, the formula is alpha AB star equal to the PA, permeability of divided by permeability of the B, right? So the value given, so 30 0.12 equal to 250, right? Now here is a R denoted by the pressure ratio. There is a pressure ratio. Right. So it's the P2 divided by P1. Here is a P1. Here is a P2. So 1.1 divided by 30. It's a 0.0367. Now we have to calculate the actual separation factors. So here is the formula. So put the value in these equations. So A alpha AB equal to 250 into XA is a 0.5. Here is the cumular measures. Right. Alpha AB minus 1 plus 1 minus 0.0367 into alpha AB. Right. X is 0.5 alpha AB minus 1 plus 1 minus 0.0367. Right. So after calculating these equations, we'll get the quadratic equations. Alpha square minus 230.7 alpha AB minus 250, right? So after solving this, so alpha is equal to 232, so which is a less than the ideal separation factors AB. So thank you. I covered all the question based on this based on topics in this included in this week's. So we will meet on the next Friday on next chapters. Thank you all.